Hello everybody, my name is Iman. Welcome back to my YouTube channel. Today we're going to tackle a practice problem set that relates to the topics we covered in chapter 1. Let's go ahead and get started with problem number 1, part A. This problem says there are 365 days per year, 24 hours per day, 12 months per year, and 60 minutes per hour. Use this data to determine how many minutes are in a month. So in this problem, we're trying to go from 1 month, all right, and convert month into minutes. How many minutes are in a month? And the goal is to use the conversion factors that we have been given to cancel out all the units but minutes so that we can go from our given quantity of 1 month into a final answer that has units of minutes. So let's go ahead and get started. We write 1 month. What's the first conversion factor we can use to cancel out the units month? Well, we know from what we were given that there are 12 months per year. So we can go ahead and use that conversion by writing 12 months in the denominator and 1 year in the numerator. And what we notice is that units of months cancels out. Now we have year. What conversion factor can we use next to cancel out year? We can use that there are 365 days per year to do that. We'll write 1 year in the denominator, 365 days in the numerator. Notice year cancels out. Now we have units of day. Okay, what's the next conversion factor that we can use to cancel out the unit day and get one step closer to getting units of minutes? Well, we can use this relationship, 24 hours per day. We can write 1 day in the denominator, 24 hours in the numerator, and notice that day cancels out. Now we have units of hours. We're getting very close. We need to do one more conversion factor now, and we can go from hours to minute. All right, we can use 60 minutes per hour to do that. We'll write 1 hour in the denominator, 60 minutes in the numerator, hours cancel out, and we're left with units of minute. Wonderful. So we were able to get rid of all of the units but minutes. And now all we have to do is do the calculation. All right, the way you can do this, input it in your calculator, is in parentheses, write out all the numbers you have to multiply in the numerator. That's going to be 1 times 1 times 365 times 24 times 60. That's your numerator. Then you're going to divide by the denominator, put all the things that you're going to multiply in the denominator in a new set of parentheses. You're going to multiply 12 times 1 times 1 times 1 in the denominator. All right, if you plug this into a calculator, solve for that, what you're going to get is 43,800 minutes, because that is the unit that was left after all of the conversions. Wonderful. Now, part B is really similar. They also want us to calculate the number of minutes in a month, and they specifically want us to use the following data. So we're going to get some new conversions that they want us to use, new conversion factors, to calculate pretty much the same thing. How many minutes are in 1 month? We're given that there are 24 hours per day, 60 minutes per hour, 7 days per week, and 4 weeks per month. So again, let's set this up properly. We start by writing what we know, what we're given, 1 month. All right, given 1 month. What is the first conversion factor that we can use to cancel the units for month? Well, we can use that there are 4 weeks per month. We write 1 month in the denominator, 4 weeks in the numerator, and notice how month cancels out. Now we have units of week. What conversion factor can we use next to get rid of the unit week? We can use that there are 7 days per week. We can write 1 week in the denominator, 7 days in the numerator. Week cancels out. Okay, what's next? We can use the conversion factor 24 hours in 1 day to get rid of the unit day. We put 1 day in the denominator, 24 hours in the numerator. Day cancels out. Okay, now we have units of hour. Let's apply our last conversion, 60 minutes per hour, to get rid of hours and get units of minute. We put 1 hour in the denominator, 60 minutes in the numerator. Units of hour cancel out, and now we have our desired units of minute. Okay, so you see how we applied the conversions we wanted in the order that we had to so that we can cancel out all the unwanted units and reach our goal of minutes. Now, for a lot of dimensional analysis problems in general chemistry, you might not be given the list of conversion factors for the specific problem, but we covered some important ones to know in the lecture. Those are ones you should definitely be familiar with. And when you are approaching a problem like this without being given the exact conversion factors, try to align the appropriate units and conversion factors in a way that will strategically cancel out unwanted units and help you reach your desired units. We'll do more practice problems, of course. Now, with the second part B, okay, to calculate the number of minutes, let's first, in parentheses, calculate the numerator. The numerator will be 1 times 4 times 7 times 24 times 60. And then divide that by the denominator. The denominator in parentheses is 1 times 1 times 1 times 1. That's all we have in the denominator anyways. Plug that into a calculator, you're going to get, there's an extra 0 here, but it should be 40,320 minutes. Okay, now this is really interesting. We have different values of how much minutes are in 1 month. And part C actually asks you, why are these answers different? Which, if any, is more correct and why? Okay, so the answer here to why these answers are different lies in the conversion factors we used. For part A, we used that 1 year equals 12 months. We know this to be exact. 365 days per year, 24 hours per day, 60 minutes per hour. On the other hand, for part B, we used a conversion factor that's not quite exact. And that is that there are 4 weeks per month. All right. 4 weeks per month means that what we're saying is that there are 28 days per month. But we know that this is not true. There are months with 30 days. There are months with 31 days. And then February is that exception. It can have 28 or 29, depending on if it's a leap year or not. So this conversion factor right here really underestimates the number of days in the month. And so when we go from this conversion of 1 month to 1 month, using the 1 month equals 4 weeks and then 1 week equals 7 days, we're doing some underestimating of how many actual days there are in a month. Hence why we got a smaller value for the number of minutes in a month. So that is where the error, quote unquote, error lies. And that means that the more appropriate evaluation of how many minutes are in a month is going to be the calculation we did in part A. We use more exact conversions like 365 days per year. This is maybe off by a quarter of a day or so, right? But in part B, we used 4 weeks to a month, which is off anywhere between 2 to 3 days. And that's significant enough to, make us get different values for part A and part B. Part A is more close to the true value of using conversion factors to get from 1 month to minutes. So that is problem 1 for us. A little bit of dimensional analysis. Let's move on to problem number 2. Problem number 2 reads, when a marble is dropped into a beaker of water, it sinks to the bottom. Which of the following is the best explanation? A says the surface area of the marble is not large enough to be held up by the surface tension of the water. B says the mass of the marble is greater than that of the water. C says the marble weighs more than an equivalent volume of the water. D says the force from dropping the marble breaks the surface tension of the water. And E says the marble has greater mass and volume than the water. So to tackle this problem, we're going to evaluate each of these options. But before we do that, you may have noticed a word that we did not cover in lecture, and that word is surface tension. This is a topic we cover later down the line, but I'm going to define just so that when we work through this problem, you have a preliminary understanding and it makes sense why we make some of the conclusions that we do. Surface tension is the property of the surface of a liquid that allows it to resist an external force, and this is due to the cohesive nature of its molecules. It's the reason why certain small objects or insects can float on the surface of water without sinking. With that being said, let's tackle this first option, option A. A says the surface area of the marble is not large enough to be held up by the surface tension of the water. Now, while surface tension can support small objects on the surface of water, it's generally not the factor that determines whether an object will sink or float. Surface tension is way more relevant for very small, very light objects, and a marble typically doesn't fall into that category. So A is not the best explanation of why the marble sinks. Let's move on to B. B says the mass of the marble is greater than that of the water. This statement is generally not very meaningful without specifying the volume of water being considered, because the mass of the marble is always going to be greater than that of a very small amount of water, but less than a very large body of water. So there's not a lot of meaning in answer choice B to really explain why the marble sinks. So we're going to go ahead and cancel out answer choice B. Answer choice C says the marble weighs more than an equivalent volume of the water. Now I'm going to tell you that this is the correct answer. All right. If the marble weighs more than the volume of water it displaces, it is going to sink. And this is just another way of saying that the marble is denser than the water. Still, let's go through the other options as well and work through the logic. D says the force from dropping the marble breaks the surface tension of the water. The force from dropping the marble does break the surface tension, but this is not the reason the marble sinks. Even if the marble were placed gently into the water without breaking the surface tension, it would still sink if it's denser than water. All right, so the key really to answering this question is making a statement, whether direct or indirect, about density being the reason why some object will sink in water or another solvent, etc. E says the marble has greater mass and volume than the water. The marble does not need to have a greater volume than the water to sink. It's the relationship between the mass of the marble and the volume of water it displaces that matters. Or in other words, the density of the marble relative to the water's density. And so this is the reason why the best answer choice is going to be C. The marble weighs more than an equivalent volume of the water. In simple terms, the marble sinks because its density is greater than that of water. So the water cannot provide enough force to counteract the weight of the marble. All right. And so when you're thinking about an object in water, you can think about it in terms of density. All right. The object will float if the density of the object is less than the density of water, and the object will sink if the density of the object is greater than the density of water. So with that, we've answered problem number 2. Let's go ahead and move into problem number 3. Problem number 3 says indicate the number of significant figures in each of the following. A says this book contains more than 1,000 pages. Okay, so for 1,000 pages, 1,000, how many significant figures does 1,000 have? Well, let's recall some important rules on significant figures, specifically for zeros. When there is no decimal, trailing zeros are not significant. So that means these 3 zeros right here are going to be not significant because they are trailing zeros and there is no decimal point. And so that means when we look at 1,000, the only digit that's a significant figure is going to be 1. This is a non-zero digit. It always counts as a significant figure. The other 3 zeros are trailing zeros, and since there's no decimal point, they are not significant. So 1,000 has a total of 1 significant figure. Awesome. Let's look at B. B says a mile is about 5,300 feet. Now, again, we have some trailing zeros here, and since there is no decimal point, these trailing zeros are not significant. The only integers that are significant are going to be the non-zero integers in this number, which is 5 and 3. So 5,300 has only two significant figures. C says a liter is equivalent to 1.059 quarts. Let's look at this number. We have three non-zero integers, 1, 5, 9, and we know that non-zero integers are always significant. And then we have this 0 that's sandwiched between the 1 and the 5. This is a captive 0, and if you remember our rules, captive zeros are significant. So actually, 1.059 has a total of 4 significant figures. And then part D says, the population of the United States is approaching 3.0 times 10 to the 2 million people. Okay, looking at this number, we have 3. This is a significant figure since it's a non-zero digit. And then we have this trailing 0, but thankfully there's a decimal place. So with a decimal point, trailing zeros are significant. So this number has 2 significant figures. Wonderful. And with that, we've answered problem number 3. Let's move on to problem number 4. Problem number 4 says round off each of the following numbers to the indicated number of significant digits and write the answer in standard scientific notation. Now, before we attempt this problem, I want to go over 2 things. I want to remind you the rules for rounding, and then I want to teach you how to write in scientific notation. Now, the rules for rounding, if the digit to be removed is less than 5, then the preceding digit stays the same. And if the digit to be removed is greater than or equal to 5, then the preceding digit increases by 1. Okay, so that's the first thing we wanted to remind ourselves, rules for rounding. The second thing is I want to teach you how to write in scientific notation. We didn't cover this in the lecture, but we'll cover it here because it's really simple. Writing a number in scientific notation involves expressing it as the product of 2 things. A decimal number between 1 to 10 multiplied by 10 to some exponent, some power of 10. All right. This notation is really useful for representing very large or very small numbers. And the best way to learn it is by doing an example problem. So keep this format in mind. You have some decimal number that's between 1 and 10 multiplied by a power of 10. Okay, so for example, what if we have this number 3,500? First thing we want to do is we want to rewrite it as a decimal number. So where can we put the decimal so that we can have a number that's anywhere between 1 and 10? If we place the decimal right here between the 3 and the 5, sorry, my pen wanted to stop working. If we put the decimal point between 3 and 5, we now have a number that's 3.5. That is a decimal number between 1 and 10. If you try other things, like if you put the decimal place after the 5 between the 0, then you have a number that's 35.0. That is not a decimal number between 1 and 10. So that's the first thing you want to do. Look at the number you're given, place a decimal point that's somewhere between 2 numbers that will give you a decimal number that is between 1 and 10. So we're going to put our decimal point right here. We get a number that's 3.5. This 3.5 is going to be multiplied by 10 to some power. How do we determine what that power is? Okay, to determine what that power is, you have to decide, okay, if my decimal point is right here between 3 and 5, it's 3.5. First and foremost, what direction does the decimal place need to be moved to get us back to our original number of 3,500? This decimal point, it needs to move to the right for us to get back our number. How many units to the right? 1, 2, 3. Okay, so we need to move our decimal point to the right by 3 places. So what that means is, if it's right, the number is going to be positive, and we figured out how many units to the right? 3 units to the right. And so our exponent here is going to be 3.5 times 10 to the positive 3. This is just telling you, hey, all right, we're moving that decimal to the right. How many places to the right? 3. 1, 2, 3. You fill in those empty places with zeros, and look at that. We got back our original number of 3,500. Let's do one more example before we tackle our problem number 4. What if you have a number 0.0042? Again, you want to place your decimal somewhere that gives you a decimal number between 1 and 10. We're just going to place it right here between the 4 and 2. So we're going to write 4.2 times 10. Okay, what is the exponent? Well, first and foremost, are we moving the decimal point to the right or to the left in order to get back our original number? We're going to have to move it to the left to get back our original number. This tells us that the exponent has to be negative. Moving to the left, negative exponent. Moving to the right, positive exponent. Okay, so we have to move this decimal point to the left. How many places to the left to get back our original number? 1, 2, 3. So this is going to be minus 3. Okay, so the number, the scientific notation for 0.0042 is 4.2 times 10 to the minus 3. Okay, now that we've covered this, let's tackle our problem. A says we have this number that we want to round to 3 digits. Okay, so what I've done here for part A is I've highlighted the first 3 significant digits in blue. Okay, and that means that this 5 right here that is right after the first 3 significant digits, this is going to be removed. Now, 5 is equal to 5, right? So we're following rule B, greater than or equal to 5, the preceding digit increases by 1. And so now if we're rounding this number to 3 significant digits, we write 0.000342. All right, that preceding digit increases by 1. Now our work is not done here. We need to write this in scientific notation. Like we said, we want to put the decimal at a position that gives us a decimal number between 1 and 10. If we put the decimal between the 3 and the 4, our decimal number is 3.42. That's perfect. Now we multiply it by 10. The next thing we have to figure out is the exponent. Now to get back our original number, what direction does the decimal place need to move? It needs to move to the left. And so we already know our exponent has to be negative. Now let's figure out how many decimal places we need to move to figure out the exact number of the exponent. To get back our original number, we're going to have to move the decimal place 1, 2, 3, 4 units, all right, to the left. So it's going to be minus 4. Our scientific notation of 0.000342 is 3.42 times 10 to the minus 4. All right, and you can always double check your work by working through scientific notation and seeing if you get your original number back. Minus 4 tells us we move the decimal point 4 units to the left. So 1, 2, 3, 4. Fill in the empty places with 0. We have gotten back our original number, so we are good. Part B says, okay, here's our number. Round it to 4 digits. I have highlighted in blue the first 4 significant digits. 7 is going to be the first number that we eliminate. If the number to be removed is greater than or equal to 5, the preceding digit increases by 1. 7 is greater than 5, which means that this preceding digit gets increased by 1. All right, that gives us 103.4 times 10 to the power 2. Now you might be thinking this is already written in scientific notation. No, remember, proper scientific notation, you have a decimal number between 1 and 10 multiplied by a power of 10. Just because this is multiplied by a power of 10 does not always mean it's in scientific notation. You have to make sure that your decimal number is also between 1 and 10. It is not, so we have to correct this. We have to correct this by deciding where does the decimal really go to give us a number between 1 and 10. The decimal place would need to be here. So we would need to write 1.034 times 10 to some number to give us what we're working with here. Now, to get back our original number, we'd have to move this decimal place in what direction? To the right. Okay, to the right by 2 places. Okay, so to the right means it's going to be a positive number, and 2 places means that that's the number we're going to add to the original exponent. So Our number is 1.034 times 10 to the positive 4. Now notice, all right, I'm going to rewrite this without all the scribbles on it. We had 103.4 times 10 to the 2. This would give us, if we expanded it out, 1, 2. This would give us 10340. Okay, and we corrected it to be in proper scientific notation by saying it's 1.034 times 10 to the 4. That means we move our decimal place a total of 4 positions to the right. 1, 2, 3, 4. We get back the same number. That's how you know you did it correctly. So always double check to make sure that your scientific notation is written properly. Okay, let's do the last problem. C says take this number, round it to 5 digits. Okay, I highlighted the first 5 significant digits in blue. All right, this 3 in red is going to be the number that we get rid of. If the digit to be removed is less than 5, which it is, nothing happens to the preceding digit. So that means we can write our answer as 17.991. Let's go ahead and write this in scientific notation. We'll put the decimal place here so that it gives us a decimal number that's between 1 and 10. So 1.7991 times 10 to some exponent. What direction does our decimal place need to move to give us back our original number? To the right, which means the exponent is positive. And by how many units? By just 1 unit. So there we have it. This number, 17.991, written in scientific notation, is 1.7991 times 10 to the power 1. Phenomenal. We've completed problem 4. Now we can move to problem 5. Problem 5 says evaluate each of the following and write the answer to the appropriate number of significant figures. So what you notice is A, B, C, we're dealing with addition and subtraction. And our rule for significant figures for addition and subtraction is that the result has the same number of decimal places as the least precise measurement. So what we want to do for A is we'll write out the addition 212.2 plus 26.7 plus 402.09. Plug that into the calculator to get the raw value, which is 640.99. Now we need to correct this to the appropriate number of significant figures. Again, for addition and subtraction, the result has the same number of decimal places as the least precise measurement. So we want to look at each of these numbers and decide how many numbers they have after the decimal place. So this one has one number, one significant figure, that's the 2. This one as well, and this one has 2 decimal places. The least precise measurement is going to be the one that has the 1 decimal place, and that means that we want to write this number to 1 decimal place. That means that the number that we're going to remove is this 9. Now this 9 is greater than 5, which means the effect it has on rounding is that the preceding digit will increase by 1. And when we do this, we'll actually be writing 641.0. So that is how we round this number appropriately to the correct number of significant figures based off of our addition and subtraction rules. B, we have 1.0028 plus 0.221 plus 0.10337. Plug this into the calculator to get the raw value of 1.32717. Again, let's figure out how many decimal places each of these numbers has. This first number has 4, this one has 3, and this one has 5. Remember our rules that the result has the same number of decimal places as the least precise measurement, which is this one. It has 3 decimal places. So that means our answer should only have 3 decimal places. The digit to be removed is this one. It's less than 5, so nothing happens to the preceding digit. And our corrected answer is 1.327. For part C, we have 52.331 plus 26.01 minus 0.9981. Plug this into the calculator to get 79.3391. Now we need to correct it. Let's figure out how many decimal places each of these numbers has. This one has 3, this one has 2, and this one has 4. Now our limiting term is the 26.01 that has only 2 decimal places. That means our answer can only have 2 decimal places. The digit to be removed is this 9, which is greater than 5. This means that the preceding digit gets increased by 1, and our final answer is 79.34. And there we have it. We have tackled problem number 5. Let's go ahead and move into problem number 6. Problem 6 reads, perform the following unit conversion. Congratulations, you and your spouse are the proud parents of a new baby born while you are studying in a country that uses the metric system. The nurse has informed you that the baby weighs 3.91 kilograms and measures 51.4 centimeters. Convert your baby's weight to ounces and convert their length to inches. Okay, so we have 2 conversions that we're doing here. For the baby's weight, we want to go from kilograms to ounces. And then the second conversion we're doing is for the length, we want to go from centimeters to inches. Now, I'll start off with the centimeter to inches one because this is an easy conversion. We only need one conversion factor in order to do this. 51.4 centimeters, you want to convert that to inches, we can use one of the conversions we talked about in lecture, which is that 2.54 centimeters equals 1 inch. We can put centimeters in the denominator, inches in the numerator. This way our centimeter units cancel out, okay? And then all we have left is units of inches. We can just carry out this mathematical operation to get 20.236 inches. Now they want you to round to the nearest quarter inch, so this can be rounded to 20.25 inches. Okay, so that's the first unit conversion they want to do. What about the second one? We want to go from kilograms to ounces. This is going to require us to use 2 of the unit conversions we talked about, and the workflow is that we can go from kilograms. We know how to go from kilograms to pounds. All right. We know this conversion. And the other conversion we know is we know how to go from pounds to ounces. So we're going to use this first to get to pounds, and then the second conversion to go from pounds to ounces. For the first conversion, we know that 1 kilogram equals 2.205 pounds. So we set this up by putting kilograms in the denominator, pounds in the numerator, and you notice that kilograms cancels out. Now you are stuck with pound units, but we can convert this to ounces. We know that 1 pound equals 16 ounces, so we put pounds in the denominator, ounces in the numerator, pounds cancel out, and we're left with units of ounces, which is exactly what we want. Now we can just carry out this mathematical operation, and what we're going to get is 137.9448 ounces. So in this problem, we were able to convert the baby's weight from kilogram to ounces, and we were able to convert the baby's length from centimeters into inches. With that being said, we can move on now to problem number 7. This is one of the more difficult problems. This one and problem 8 are going to be more challenging problems, but we're going to break it down together, so do not worry. Problem 7 reads, mercury poisoning is a debilitating disease that is often fatal. In the human body, mercury reacts with essential enzymes, leading to irreversible inactivity of these enzymes. If the amount of mercury in a polluted lake is 0.4 micrograms of mercury per milliliter, what is the total mass in kilograms of mercury in the lake? The lake has a surface area of 100 squared miles and an average depth of 20 feet. Okay, so what are we given with to start off? 0.4 micrograms of mercury per milliliter. What do we want? Mass of mercury in kilograms. So something you're noticing here is that the units for mass is being converted from micrograms to kilograms. This milliliter quantity, this volume quantity has disappeared. And this actually gives us a hint to what we have to do first to ultimately convert this concentration we're given. This is a concentration, mass per volume, all right, into just mass of mercury. So the first thing that we're going to have to do is we're going to have to multiply this concentration, 0.4 micrograms of mercury per milliliter of water, by the volume of the lake. And this arises from the definition of concentration itself. Concentration is a measure of how much of a given substance is contained in a certain volume. Here, that substance is mercury. Here, that volume of solvent is the lake water. So, to first find the total amount of mercury in the lake, we're going to have to take the concentration and we're going to have to apply it to the entire volume of the lake. So the first thing that we're going to do is we're going to take this concentration we're given, All right, 0.4 micrograms of mercury per milliliter. We're going to have to multiply it by the volume of the lake, all right, in milliliters. That way, we get rid of this volume term, and then all we have is going to be the mass of the substance, the mass of the mercury in micrograms still, and then we can worry about converting micrograms to grams and then from grams to kilograms. All right, so the first part, first and foremost, we want to get the mass of the mercury. Okay, and to find the total amount of mercury, first and foremost, we're going to have to multiply our starting value of concentration by the volume of the lake. Now, you might be wondering, how are we going to find the volume of the lake? That's our first step. Well, we're given some good information. Okay, we're given the surface area and the depth. Now, if you remember, volume is just length times width times height. We are given the depth. You can think of that like the height. That's 20 feet. All right. And we're given the surface area, 100 squared miles. This is like the length multiplied by the width. Here's the first problem. They're not in the same units, so we can't just multiply them with each other to get the volume. First thing we want to do is we want to convert this 100 squared miles to squared feet. And we know how to do this because of a conversion we covered in our lecture. We know that 1 mile is equal to 5,280 feet. So we set it up like this. We write 100 squared miles. We're going to multiply this by our conversion factor. Notice that our conversion factor is in parentheses here. We're going to do something to this, and I'll explain it in a second. Our conversion factor is that 1 mile, we put that in the denominator, is equal to 5,280 feet. And that's good because our miles are going to cancel out. But here's one thing. This is squared miles. Right now, this is just miles. So technically, we would only be canceling just one of these miles. But we want to cancel out both. And in the end, we want our units to be squared feet anyways. So we're going to square this conversion factor. This way, this square goes to the number and to the unit. So technically, what does this look like? I'm going to erase this really quickly. What this looks like is that we're squaring 5,280 and we're squaring feet. We're squaring this one and we're squaring miles. And what you notice is that miles squared will cancel out. Okay, and then we're going to get our answer in units of squared feet. So this way we have converted 100 squared miles to squared feet. This is a large number. Now for volume, we can take this number, multiply it by the height or the depth, which is 20 feet. And this way we get the volume. The volume is going to be in units of cubic feet. Okay, cubic feet, that's okay. We can't multiply the concentration by cubic feet because cubic feet and milliliters, they're not in the same units for volume. So our second big step is to convert our volume into units of milliliter. This is a little tricky, but once you get the hang of how you can go from cubic feet to milliliters, or even going from cubic inches to milliliters or cubic centimeters to milliliters, it's just going to be a repetition every time you encounter this kind of protocol. So we're converting cubic feet to milliliters. We didn't talk about a direct conversion from cubic feet to milliliters, but we did talk about a direct conversion from cubic centimeters to milliliters. All right, we know that 1 cubic centimeter is equal to 1 milliliter. So then the question becomes a little bit easier. How do we get from cubic feet to cubic centimeters so that we can then apply this conversion? Well, we can convert feet to inches. 1 foot is 12 inches, and then we can convert from inches to centimeters. 1 inch is equal to 2.54 centimeters. So this is the way that we're going to approach the conversion. The only thing to keep in mind is these units are cubic units. So whenever we're doing these conversions, we have to make sure that we cube the conversions as well to make sure the units cancel out properly. So we can start off by writing our volume in cubic feet. That's shown right here. All right, these numbers are big, so I'm not reading them out loud, but you can view them on my screen. So here's our volume in cubic feet. First conversion is we're going to go from feet to inches. 1 foot is equal to 12 inches. Great. We have to make sure that we cube this conversion so that cubic feet can cancel out properly. Okay, so we make sure to cube this conversion as well. Awesome. Now we have cubed inches. We can go from inches to centimeters. We know the conversion, that 1 inch, we put that in the denominator, is equal to 2.54 centimeters. Again, we have to cube this conversion because we have cubed inches over here. So we need cubed inches over here so that they can properly cancel out. What are we left with? We're left with cubed centimeters, cubic centimeters. This is great. Now we can use our conversion that 1 cubic centimeter equals 1 milliliter. And that's our final conversion to convert our volume from cubic feet to milliliters. Now, the next thing we do is we can multiply our concentration by the volume in milliliters. This is going to give us an answer that's just micrograms of mercury. And then the final 2 steps is just to convert micrograms of mercury into kilograms. The first conversion we can do is we can convert micrograms to grams. 1 microgram is 10 to the minus 6 grams. And then we can convert grams to kilograms. 10 to the 3 grams equals 1 kilogram. And you can carry this whole mathematical operation at once, hence why I have it set up like this. We get rid of the volume term first, all right? And then we convert from micrograms of mercury to kilograms of mercury. And our final answer should be 631,542.7 kilograms. That is the total mass in kilograms of mercury in the lake. With that, we can move into our last and final problem, problem number 8. Problem 8 reads, a 25-gram sample of a solid is placed in a graduated cylinder, and then the cylinder is filled to the 50 milliliter mark with benzene. The mass of benzene and solid together is 58.8 grams, assuming that the solid is insoluble in benzene and that the density of benzene is 0.88 grams per cubic centimeter. Calculate the density of the solid. So in this problem, we're presented with a scenario that involves determining the density of a solid by using a liquid, benzene, as a displacement medium. And the task is to calculate the density of the solid given the combined mass of the solid and benzene and the density of benzene alone. So what we first want to do is work a bit backwards. So we can find the mass of benzene. Why? Because we're given the total mass and we're given the mass of the solid. And then from there, we can take that mass of benzene and using the density, find the volume of benzene. The reason that this is important is because ultimately we can take that volume of benzene and the total volume, which is 50 milliliters, and subtract the two. 50 milliliters minus the volume of benzene gets us back to the volume of the solid. Now, if we have the volume of the solid and we're given in the problem the mass of the solid, then to figure out the density of the solid, we just divide mass by volume. So we're going to do this workflow to ultimately get to the one piece of information we don't have, the volume of the solid, and then take the mass, take the volume of the solid to calculate the density. But of course, like I said, that involves these preliminary steps of figuring out mass of benzene, volume of benzene, and then finally figuring out the volume of the solid. So let's go ahead and get this started. Let's find the mass of benzene. We know the total mass to be 58.8 grams, all right? And we know that the mass of the solid is 25. So to figure out the volume, figure out the mass of the benzene, we're simply going to subtract the total, 58.8 grams, minus the solid, 25 grams, to get 33.8 grams for the mass of benzene. Wonderful. Now let's figure out the volume of benzene. How do we do that? Well, we can use density to calculate the volume. We know the mass is 33.8 grams. We can use density by putting 0.88 grams in the denominator, cubic centimeters in the numerator. This way grams cancel out and we get our final answer in cubic centimeters, which is a measure of volume. When we do this, we get 38.41 cubic centimeters. Remember that 1 cubic centimeter equals 1 milliliter. So 38.41 cubic centimeters is equal to 38.41 milliliters. This we're going to use for the next step. The next step is to figure out finally the volume of the solid. We know the total volume is 50 milliliters. We figured out the volume of benzene. Now we can just subtract 50 minus 38.41 milliliters, gives us 11.59 milliliters. And then to finally solve the problem and get the density of the solid, we'll put the mass of the solid over the volume of the solid. 25 grams divided by 11.59 milliliters gives us a density of 2.16 grams per milliliter. We can also write this as 2.16 grams per cubic centimeter. And there we have it. We figured out the density of the solid. And with that, we've actually completed our practice problem set that relates to chapter 1. Let me know if you have any questions, comments, concerns down below. I really hope this was helpful. If you have more problems you want to see, feel free to send them my way through email, which is linked in the description box below. And I will hopefully be able to collect maybe another set of practice problems for chapter 1 and cover that for you. Other than that, good luck, happy studying, and have a beautiful, beautiful day.